Hello, this is our first short video in Module 5 on amines and heterocycles. The structure and bonding of amines is similar to alcohols, except substitute nitrogen for oxygen, generally speaking. If you look at the flagship amine, ammonia, it's sort of like analogous to water for oxygen. So all of the single bonds coming from nitrogen are sp3 hybrid orbitals, along with the lone pair itself being in an sp3 hybrid orbital. Therefore, all the bond angles are approximately 109.5. A little bit different because of the lone pair, probably. These three bonds here will be pushed down slightly, so maybe a little less than 109.5 there. And so there, it's obviously it's tetrahedral around nitrogen, always considering a lone pair, never not forget about that. Here we have more of the standard appearance of an amine, and we call the terminal group an amino group. So there's more nomenclature for amines. The traditional primary, secondary, tertiary. It's actually a little easier than for alcohols. So essentially you're looking at the groups attached to nitrogen, and for a primary amine, there's one group on the nitrogen, an N-butyl group, so we simply call it N-butylamine. It's kind of similar to the nomenclature of ethers, where you just say methyl, propyl, ether, for example. A secondary amine has two carbon groups attached to the nitrogen, and so some nomenclature practice here: methyl, N-propylamine. Tertiary amine, three groups on nitrogen. We would call this dimethyl N-propylamine. There's a sort of a weird special nomenclature for nitrogens that have a fourth bond, which they can certainly do using that lone pair, form a fourth bond. And notice this is similar to ammonia, but the common name for this is a quaternary ammonium salt. So quaternary comes from the four bonds, but it's not really consistent with the nomenclature for primary, secondary, tertiary. But that's just what it's called. So any nitrogen, for example, a nitrogen in a fused ring system like this that has a fourth bond, it'll always have a charge. It's not necessarily paired up only with chlorine, it could be other counter ions, but we would also call that a quaternary ammonium salt. Reactivity of amines. Clearly, amines are Lewis bases, and they also have polarized bonds. So the nitrogen's more electronegative than these hydrogens, so we'll have a delta minus, delta plus effect, inductive effects there due to electronegativity. Likewise, delta minus, delta plus when we look at the nitrogen to carbon bond next to it. And so the Lewis base reactivity is simply electron pair donation, electron pair bond forming, classic Lewis base. Clearly, we'll look at examples shortly here where it can act, amines can act as both either a base or a nucleophile, right? And so hydrogen bonding, because of the inductive effects and electronegativity, hydrogen bonding is important for amines, just like for alcohols. And in this scheme, we can see that you would probably have a hydrogen bond here. So you're looking at the interaction between lone pairs and hydrogens. And remember, this is delta plus, so makes sense. And then likewise, the lone pair on nitrogen could hydrogen bond. So this is a case where we're looking at basically that if amines are in an aqueous solution, for example, that they would be surrounded by water molecules, and there would be a lot of hydrogen bonding going on with all of the implications of that. So that's something to keep in mind. Hydrogen bonding in amines is extremely important in biochemistry. Now, mentioned earlier, if they can act as Lewis bases, amines can act as nucleophiles. And here we have a classic nucleophilic attack on a carbonyl. And so we have arrow pushing like this. That will form this intermediate with charged species, oxygen, nitrogen, as you see. This proton loss, proton gain, to get to the final product, it's just proton transfers. It could occur via other things floating around in solution, or internally, potentially. You could have sort of something like this going on if the geometry is such that it allows it. And so either way, you get to this material, right? And this has all the hallmarks of a nucleophile that has added to what was once a carbonyl. Remember that often we want to do retrosynthesis to say, how do we make something like this? Well, we can recognize that that bond would have been formed by an amine nucleophile attacking a carbonyl carbon, resulting in an alcohol there. Lots of similar examples in synthesis. This process can continue, though, if it was, for example, in acid conditions. Here, we can protonate the alcohol, resulting in that OH2 excellent leaving group, right? And it's like an elimination, it's like an E2 elimination reaction. So, say there's some more water present. This can be deprotonated. These electrons go here and kick off the excellent leaving group into a sea of water. And so we create an imine. We call this an imine. Notice how likely this is to be similar to the reactivity to a carbonyl group. Right? It's the same electronic setup. In fact, even better in some ways, because the nitrogen has a plus charge, and so, for example, a nucleophile could come in here, kick these electrons up, and where are they going? Toward a full plus charge. So I'm just going to put that in parentheses there. Similar reactivity. Expected. So here we have a nucleophile doing exactly that, right? Electrons coming in, kicking up, and that leads us to this. So what did we really just see is we saw the creation of an imine through the addition of a nitrogen nucleophile to a carbonyl. Then we could add to create an imine, and a nucleophile could come in. And so we've accessed molecules of this sort, where now the nucleophile could be virtually anything, like a whole big carbon group, for example, a Grignard reagent with a big carbon group on it. And alternatively, if you don't want to, if you're ready to stop at this earlier point, you can just reduce the imine and stop there. Our primed, our double primed, they could all be the same or different. And so that's our brief introduction to that. We're going to continue along this same vein with the creation of imines, followed by, in this case, their reactions with an enolate which is a nucleophile, as we know, and that happens to have the name reaction, the Mannich reaction.